Hi, this is Prasanna from Wave Academia. In this video, we are going to see about controller tuning using closed loop Ziegler-Nichols method. These rules were first proposed by Ziegler and Nichols, who were engineers for a major control hardware company in US. Based on their experience with their transients from many types of processors, they developed a closed loop tuning method. Still, they used in many industries. So this method is described as a closed loop method because the controller remains in the loop as an active controller in automatic mode. Okay, so in this video I'm going to take the transfer function of gp is equal to 1 divided by 5s plus 1 into 2s plus 1 into 10s plus 1. So this is my system which will be represented as a transfer function model. I'm going to calculate Kp, Ki, Kd for this transfer function. Let us see how to do that. I'm straight away going to the Matlab. I'm just opening a transfer function. So transfer function numerator value is 1 and denominator value, you cannot straight away give this transfer function denominator value 5s plus 1, 2s plus 1 into 10s plus 1. You have to cross multiply and you have to substitute in the form of s cube term, s square term, s term and then constant term likely. So here if you multiply this you will get 100 s cube plus 80 s square plus 17s plus 1. Apply it. I need a PID controller. I will tell you how to do that operation. The feedback is a negative feedback. I need a step input. Let it be input is step time is 1, initial value is 0, final value is 1. I want my system to be settled at final value of 1. So I want to see the scope, output through scope. Now the measured value is compared with the set point with the help of comparator. This one is my transfer function, my plant, and this one is my PID controller, and this one is nothing but a sum which will give you the comparator output, and this is my reference point or set point. Okay, there is a procedure in Ziegler-Nichols method. This method did not suggest that the ultimate gain and ultimate period to be computed from frequency response calculations based on the model of the process. Here I will tell you what is ultimate gain and ultimate period. There is a procedure. Once the process reaches the steady state at the normal level of operation, remove the integral and derivative controller modes from the controller. If you look at this, if you double click this, you can able to see proportional, integral and derivative controllers are there. So what you have to do is you have to remove this integral controller, say it is 0, and derivative controller also 0, and allow only PID controller in the closed loop. I'm clicking apply. Okay. After that you have to keep on checking the response until your response reaches sustained oscillation. What is sustained oscillation? Oscillation with fixed frequency and amplitude is called sustained oscillation. So if you look at this, in this controller, you have to keep on this increasing the proportional gain value until the system response reaches sustained oscillation. The value of gain and the period of oscillation is called ultimate gain and ultimate period. Here, the ultimate gain is a measure of difficulty in controlling a process. Higher the ultimate gain, which is easier to control the process, whereas ultimate period is termed a measure of speed of response of loop. Larger the period, which slower the loops. Okay, now we'll see. Look at my PID controller. My integral gain is 0, derivative gain is 0. So I'm starting with my proportional gain of 1. If you want a better output, just go to modeling, go to model settings, because we are working on response, sinusoidal response. Go to solver details, change this maximum step size as 0.01. It will give you a better response. Now simulate the process. If you look at the output, yeah, still we need to do, we need to keep on increasing the KP value. Say it is 5. Apply it, okay, run the program. Not yet. Change the value to 10. Click OK. Again simulate the program. Yes, it's about to get the sustained oscillation, but still we have to tune the value. So this is a closed loop. Okay. Now I'll tell you what is the ultimate gain is 12.6. If you keep on doing this, definitely you will get sustained oscillation at this value. 12.6 is my gain value. If you run the program now, yeah, of course, this one is the sustained oscillation, means a fixed amplitude with fixed frequency. Now, the gain of the sustained oscillation is called as ultimate gain, whereas the period of oscillation is called ultimate period. How to check the period of oscillation? Select the bi-level measurements. Go to cycles. If you look at this, the period of oscillation is nothing but for complete one cycle, it giving you 15.234 seconds. So this will be called as period of oscillation. So we know period of oscillation, that is nothing but ultimate period PU, and we are having ultimate gain KU. Now I'm going to my PPT. So once you got the ultimate gain as well as ultimate period, now use this Ziegler-Nichols tuning table to find out the KP, KI, KD for the given system. So if you are using proportional controller alone, KP is 0.5 into KU. If you are using PI, 0.45 into KU is KP value. PU divided by 1.2 is tau I value. Here, tau I is nothing but integral time, but Matlab input requires as the input of Ki. Ki is integral constant, whereas tau I is integral time. How to relate tau I with Ki? Ki is equal to 1 by tau I. You should be very careful about this mathematical representation. If you give tau I as an input in Matlab, definitely you will get a wrong output. Okay, the input should be ki, not tau I. Tau I is integral time, whereas ki is integral gain. Integral gain is inversely proportional to integral time. Similarly, in Ziegler-Nichols tuning table, you will get only tau d. What is tau d? Tau d is nothing but derivative time. But here you can directly give this tau d as a kd. Actually, tau d is equal to kd. That means derivative time is having a direct proportionate with derivative constant. Okay, so from the response we know what is ku, okay, and then what is pu. Now if you substitute this ku and pu in this table column in such a case that if your controller is PID controller, take this one. For kp, that is proportional gain, 0.6 into ku, integral time pu divided by 2, derivative time pu divided by 8, which will give you kp, ki, kd for the given transfer function. Okay, so again I am repeating. So in the case of Ziegler-Nichols closed loop tuning, once the process reaches steady state at the end of the normal level of operation, remove the integral controller as well as derivative controller from the PID and leaving only the proportional control. Now keep on increasing the value of proportional gain until the system reaches sustained oscillation. The gain value of oscillation is called ultimate gain, whereas the period of oscillation is called ultimate period. Once you obtain this ultimate gain and ultimate period, you can easily calculate Kp, Ki, Kd for your transfer function using Ziegler-Nichols tuning table. Okay, now if you calculate those values, Kp is 7.4, Ki is 0.132 and Kd is 1.89 for this given transfer function. Okay, now let me substitute these values in the controller. Now go to Matlab, go to the process, PID controller, select the values accordingly. So now change the Kp value as 7.4 and integral value as 0.132, derivative value as 1.89. Apply. Okay, now if you execute the program, just if you want to see the output, increase the simulation time. Now you will get the set tilt output for the given transfer function. Yeah, as I said earlier, both scientists Ziegler and Nichols did not suggest that the ultimate gain, ultimate period be computed from frequency response calculation based on the model of the process. Actually, they developed this transfer function, this tabulation model from their experience on so many transients. Okay, when they imposed their rules for the first time on those times, frequency response methods and process models were not generally available to the control engineers on those days. So they employed this kind of procedures. But nowadays, we are having so many frequency response methods, especially if you take body, you can easily calculate what is gain margin, phase crossover frequency, gain crossover frequency. Actually here from the body, you can easily able to get this omega C naught value. Actually omega C naught value is nothing but it's a gain crossover frequency. Okay. So this is nothing but the frequency of sustained oscillation. Once you get the frequency of sustained oscillation, you can easily calculate the time period of sustained oscillation. Okay, so we can easily calculate omega C naught from the frequency method example body. That's what we're going to see now. I'm going to my Matlab. I'll open a live script. So we know that we are having a transfer function like 1 by 5s plus 1 into 2s plus 1 into 10s plus 1. I'm going to simulate the same transfer function using M file. Let it be numerator is equal to 1, denominator is equal to, you have to mention same like 100 s cube plus 80 s square plus 17s plus 1. System is equal to transfer function of numerator comma denominator. If you execute this one, you will get the transfer function. Because it's a live editor, you can able to see the output here. Okay, now I'm going to calculate what is my gain margin, what is the gain margin, phase margin, gain crossover frequency, phase crossover frequency for the given system. How to do that? This is the syntax. GM represents gain margin, PM says it's a phase margin, WCG will give you gain crossover frequency, WCP will give you phase crossover frequency. So that is equal to margin of system. Now if you run the program, you will get the output like this. Look at here. The gain margin of system is 12.6. Actually, this is nothing but your ultimate gain. This value is equal to ultimate gain, KU. Here, gain crossover frequency is given as 0.4123. So this is nothing but actually omega C naught. Gain crossover frequency is nothing but the frequency of sustained oscillation. So from this omega C naught, you can easily calculate PU. What is PU? PU is equal to 2 pi divided by omega C naught will give you period of oscillation in radian per seconds. Sorry, in cycles per minute. Okay, so 2 pi divided by omega C naught will give you period of oscillation. So this is available in this PPT. So from the body plot, we are having KU as well as we are having omega C naught. Once KU and omega C naught is available, from the omega C naught, you can easily calculate PU. The same way, once the KU and PU are available, whatever the controller you are employing, you can take this as a reference to calculate proportional gain, integral gain and derivative gain with respect to your system. Again, now if you once you calculated the values, substitute the values in this PID controller, it will give you the same kind of output. Okay, values should be very same. So whatever things we discussed close to PID tuning using Ziegler-Nichols method. Again, I'm repeating the procedure. Once the process reaches a steady state at the end of the normal operation, remove the integral controller as well as derivative mode, leaving only proportional controller. Now keep on increasing the proportional gain value until the system reaches sustained oscillation. Sustained oscillation means oscillation with fixed amplitude and frequency. The gain value of sustained oscillation is called ultimate gain and the period of oscillation is called ultimate period. Once Ku and Pu are calculated, then you can use this tabular formula to find out Kp, Ki, Kd for the given transfer function. The second, we can use Bode to calculate the Ku as well as omega C naught. Both method will give you same kind of results. Hope this video will be very helpful to you to solving the Kp, Ki, Kd for the given transfer function. Thank you. Kindly subscribe the channel.